picture me eating. Binary explosives.
And then the other thing is you need to know when the rejection is coming off person's parts.
Yeah,
You just do one summation for each section.
Okay. So I just add these 5.
It was a very weak and
That's alright.
no one suffered of falling trees. It's good. I noticed about 3 homework submitted by email. Are there any in print submissions? Okay. If maybe I missed some emails that were going on while I was coming here.
Because that was just the YouTube videos, right? Just emailing you the videos.
And a couple of snapshots of the images with explanations.
Oh, I did not.
I didn't sign
I
that
just
part.
did the.
I just
did the video.
I just
Sorry.
emailed
No, not a problem. Not a problem. It's like I don't know, 5-10 minutes.
Okay, I'll just do it later.
Yeah, no problem. So who we are and what are we doing? Waiting until the Christmas break. Suffering as less as possible. It is a course of physical chemistry. You want to predict outcomes of experiments and measurements from instruments. And we take into account wave nature of electrons that has some quantum laws. And then we are applying these quantum laws to a certain ladder of systems in level of complexity, because if we do something realistic, it will be not possible from scratch. So right now we are, what are we considering? Huh? For which system? For box, right?
Yeah.
And is this box, what is the initial state? You can tell us what was the initial state of the particle in the box. So what was the initial state? It's a question to you. What was the initial state?
Oh. Initial state of
Particle in the box that we are considering in class and in homework.
in the center box.
Okay, and if you if you speak about distribution in space, and if you speak on language of quantum states, was it either one of eigenstates or not? What was specific about the problem that we are solving? Both related in homework and in a couple of lectures class. So there are 2 answers. Was it an eigenstate or not?
It is. It is an eigenstate.
Or not?
I think it is.
Okay, who is that initial state for the problem we are solving was an eigenstate? Who is, raise your hand. 1? I specifically like what you do. Raise the hand who is that it was eigenstate. Okay, who will vote that it was not an eigenstate? 1, 2, 3, 4. Okay, majority. It was not an eigenstate.
Which one is like smaller, right?
Huh?
Once the box is, we're going to talk about like the box getting smaller, right?
No. Those are 2 different things.
Oh, okay.
There is one that how the energy of the state depends on the size of the box, right? The smaller the box, the higher the energy. And historically, everyone is getting very happy and getting this idea very quickly. But now we are coming to the second idea. What if we are looking for non-stationary, for dynamics? And if we take initial state as the eigenstate, it's boring. There will be no dynamics because from postulates, if isolated system is created in one of the eigenstates, it will stay there forever. So we are looking what will happen if the system is not in the eigenstate, but it is initial state is summation of two eigenstates. So it is solution, but it is not an eigenstate, right? So more specifically, what was the initial state? Huh?
No.
Which quantum states of particle in the box you know? Or if you need to, I don't know if there is a like cumulative or oral cumulative exam, if there will be general knowledge check, if someone asks you which quantum states do you know, and you can answer very generally. There is a general answer that you feel in any circumstances. It does exist for any system. Lowest energy. Sometimes it is not one. Sometimes there is more than one electron. But equilibrium, or there is a yes, exactly. So ground state. And if the eigenstate is not ground, how we can refer to it?
Excited.
Yes. And we take ground and the lowest possible excited state. And then we prepare system in superposition of those. So they are like 50-50 composed of both of them. And then we are following what will be the dynamics in time, how things will proceed. Right? So it is what you were thinking all the weekend and memorizing, and oh yeah, I like to predict future of the superposition of states. Okay. And how were we solving this problem? Which of the ways to predict future we were using? Time-dependent expansion of our eigenstates. Okay. For wave functions, wave function is trivial. You just write one line. But wave functions are not you cannot observe. And we need either to target something that is potentially observable, like probability distribution, or exactly observable, some that can be measured in experiment. We postpone any observables and just focus on probability distribution, which is wave function exploit. So, did you remember any new information from Friday? Which color it is symbolized with on this diagram? Huh? Do you see this method? Huh?
Red?
Yes. There are two reds, so probably far right, red, top right, red. So, what is density matrix and why it is helpful in predicting future of this superposition state? Can we live without it? Yes, we can. It's not a necessary concept. It just makes life a little easier. But in which sense? Do you have any feelings or memories? So we applied Euler to time dependence. What you're talking about, right? Accumulation of phase. But before that, it's a tough question. I barely answer myself. So it is a concept that helps to chop solution of the time-dependent and space-dependent parts, and it is just is more organized. You can get quicker to the answer, and you already know the answers from your movies. right? So and we were looking at the movies in class as well. So this distribution changes having maximum either more to the left or more to the right. And in very approximate way, it corresponds to classical particle bumping into the wall, reflecting, reinforcing back. Right? Make sense? Okay, so you're already done with main message of today's meeting, and I will try just to add a little bit more details. But if you agree with the statement and you feel that it's a good idea, you can win back and relax. See if this, yeah, this works. So it is the summary of things that we already discussed, right? So there is a ground, which is camel with single count, and excited with camel with 2 counts. And it is a superposition in those. And we look to see how the probability distribution will look if we add them together and if it is allowed to go forward in time. So it is always very not confusing, but it's a source of feeling bored and a big temptation to fall asleep and skip everything, because I remember myself, it always looks like the models discussed in class are very far from real life. Why should I spend time focusing on them? And the connection of this model to the real life, it is something that we were discussing, but I wouldn't be surprised that your busy schedules washed out memories about this. So particle in the box is a model for conjugated oligomers, right? Or for two-dimensional thin films of semiconductors. Dielectric and semiconductor between them. So this is sun that creates excited state, and electron hole can move between these blocks. So this the problem that we are solving is very far related to like photovoltaic panels. Not directly, but there is some relation. And this is the thing that we are doing. So we are finding the distribution that we need for the distribution as product of the spatial part and time part, where those indices are orbitals that are which trigonometric functions? Sine and cosine. Huh? Sine in for our selection of boundary conditions. If you select boundary condition from minus L over half over 2 to L over 2, then it will be cosine. It doesn't matter, they're interchangeable, it depends on the source. But in our system of coordinates, also sine. And this time-dependent part is often referred to as density matrix, and it is composed of the initial expansion coefficients, which were selected in our case as 1 over square root, right? Doesn't surprise us. And the accumulation of phase, so since this object focuses and tracks together 2 orbitals, right? There are 2 indices, 2 initial expansion coefficients, and 2 energies. So it accumulates not the phase of a single orbital, but it tracks the phase difference between 2 orbitals. And we will see later if the indices coincide, then phase difference will be zero. No phase accumulation. If they are different, then there will be the same some phase accumulation. Next year we not just went back into that, but next year probably it will be the right place to make a little quiz to remember this equation, right? Which I have no doubt you are going to. Right? So energy of state is inversely proportional to size of the box squared and the number of states. So let's practice. I think I'm going to click until the mission level. I hope you don't mind. So if you practice this expansion and our indices I goes from 1 to 2 and j runs from 1 to 2, then total number of terms will be 4, right? And here we do have the time dependent parts, and here we have spatial parts, right? So products of orbitals. If it is the first orbital, it will be this single camel squared. If it is excited state, it will be double camel squared. And if it is coarse terms, fourth diagonal terms, it will be products of the sign of the x and 2x, right? So the time accumulation will be trivial for ground and excited because energies subtract the orbital the same, right? And if the energies are different, then one cannot cancel. There is a phase accumulation. If you do not have a computer, do you feel comfortable to plot this? No. But do you think you can simplify it so that one can plot it and avoid using computer, like doing the stuff that you did in lab and in homework without any computer, just getting general. So our what? Not super organized today. What is the goal? What is the purpose that you want to achieve today? You already know that the answer is the distribution of the packet that kind of bumps into left and right wall and performs oscillations. We did it in simulation, but we wanted to get the same result just by pen and paper. We want to see that as time goes by, there will be maxima winning towards left, towards right, or staying approximately in center. So if you get these functions, the goal for today's meeting will be achieved. Okay? And basically, this function should give us this result. It is just a lot of discomfort to plot it. I'm not seeing it immediately, but maybe there are some manipulations to simplify it. So what is mostly irritating in this writing? Huh? Exponent, and especially that exponent is imaginary. I was going to joke that most irritating of this expression is this expression itself. Necessity to look at it. And do you see any errors or typos? I don't. Let's just double checking. There is minus and minus here, but the orders of indices are swapped here. I just for a second started to be confused because if one keeps the same thing in the bracket, then we need to swap the same. Okay. So the energy here is the same by absolute value. And if I'm lazy, I can call it like delta E, minus delta E here and plus delta E here. Is there any difference? Do we see any difference between this spatial part and this spatial part? So it looks like you can take it out of brackets, right? And then add together these two exponentials. So it is basically what we discussed on Friday. What Kristen mentioned under density matrix is connected to Euler. Okay. So if we add together these two exponentials, then by Euler we should get what? If there is a plus between them, it will be cosine. If minus, it will be sine, right? You agree, you do not need to put this little thing. If you do, give me a little sign. No? Okay.
Nothing new.
Okay, so the cross term, we put this sine x and sine 2x out of brackets, and then we have a summation of two exponentials. And they give us a cosine. So right now, maybe last year I was explaining to someone what is cosine, because this one consists of sine and cosine, and this one consists of sine and cosine, and sines cancel each other. So this stuff simplifies to cosine, and what? So here we get rid of exponential to the power 0, right? It's just 1/2. Where 1/2 is coming from? Huh? Yes. So initial condition is 1 over square root of 2. And here you have expansion coefficient squared, right? Or one can interpret it, since it is probability, it's like 1/2, 50% that it is in ground, 50% that it is in the excited. And those will be like diagonal density, which is easy to interpret by human intuition. But in addition to this diagonal density, there is a transition density, which is non-zero only if there are superpositions, if system is in a process of going from one state to another one. And Alyssa should be happy about this term, because transition density is a key component of TDDFT. So, regular density, transition density. There is no time dependence here, so it will be some constant terms. And here we have oscillations. Cosine of this delta E times time and divide by Planck constant. How can we interpret this cosine? What does it mean? How the again, our goal is to plot this expression. If we make snapshots at different point of time, what are snapshots of cosine function? Numbers that are limited between which boundaries?
-1 and 1.
Huh?
-1 and 1.
Yes. Yes. So if we plug in specific value of time, we will get either +1, -1, 0, or something in between, right? And basically, if you take +, -1, +1, -1, and 0, it will be limiting cases. Anything else we can interpolate just by human brain how to look in between. So basically, what I suggest, we will select such values of time which will bring this cosine function into +1, -1, or 0. Right? So cosine starts at 1 and makes full period. It is 0 when the argument of cosine is pi over 2. It is negative when argument is pi, and it is sufficient for us. So suppose we focus on argument of cosine equals pi. It means that energy difference divided by Planck constant multiplied by unknown time will be equal pi. Okay. Can we solve it for t? For time. This one is equal pi. So just right here. So we inverse, and time will be pi h bar over energy difference. So if time is equal to this duration, then cosine that pops up in this expression will make half of the oscillation. If we have double that, if we put number 2 here, it will be full oscillation. If I want to practice calligraphy and write something reasonable about this slide, what should be my notes? Especially about this box. So let me formulate the question. Is there any connection between period of oscillatory motion in the system and energy offset of the levels? Full period with T capital will be equal to pi h bar divided by first. Once again, because I'm famous calligrapher, practice on screen. Pi h bar delta. So the question is there any connection between period of oscillations and energy offset between levels? Huh? Mm-hmm. Exactly. So any quantum system in superpositional state has its own property to perform oscillations. And oscillations will be very quick if energy offset is big, and will be slow if energy offset is small. I don't know, because you proved it. It's what comes from here. Because of phase accumulation is proportional to difference in energies, right? So, and this phase accumulation just through our body Euler gives this cosine oscillations.
I guess just physically, why would it go slower between ones that are closer and faster?
Okay, you want not explanation but interpretation.
Yeah, the math is right.
I have engineering explanation that I'll postpone, and it is very clear, and I'll try to build something that is not quite clear. If two levels are very close, then their oscillation frequencies are very close as well. It means they accumulate phase almost at the same place. In the limiting case, if the frequencies coincide, then there will be no motion at all, right? As we saw for eigenstate. Or if you put degenerate state, two states of the same energy, their phase accumulations will cancel. There will be no motion at all. And in one case, we have some motion. In another case, there is zero offset. We have no motion. In the limiting case, it will be slow, very slow motion.
Okay. So essentially, they're like phase conditions.
It's absolutely perfect.
Okay.
I cannot say it better. Please repeat.
Yeah.
I need to learn it.
Their phase accumulation is so similar that you can notice the difference.
So similar that difference takes longer.
The words aren't
It's normal. Very good, very good. I think you re-established peace in the audience. It takes so long to notice the difference because the frequencies are very similar. Okay.
Just like, okay, physically, right? Like, if an electron is jumping between one state and the other, like, just like moving, wouldn't it take longer time for it
To notice the difference.
versus the. So why?
So reason of
Oh, that's interesting.
Yeah, because like if physically, like if you're thinking about just like a gigantic scale of it, right? You're talking about your energy, like low energy state, high energy state. And if they're further apart, why doesn't it take more time to go back and forth between them versus when they're smaller? Because it could easily just the energy, like I guess the activation energy isn't as high.
Okay, I want to make a disclaimer which doesn't literally answer your question, but maybe you will formulate your question. What we are doing is far too related to transitions between states. But in fact, what we are doing right now doesn't have any transitions. We do have superpositional state between ground and excited, and proportion 50-50 doesn't change. We're not looking how quick it will jump from ground, how quick it will excite or de-excite. It is, I'm intentionally selecting this subject because it is very paradoxical for human brain.
It's kind of like, well,
Simultaneously, yes.
it's kind of like in the box, it's like everywhere. For like an electron cloud, it's kind of just everywhere.
I'm good. Keep
Okay.
going.
Oh, thank you.
Yeah, so that's really
So it's a really good take-home message that I was forgetting to highlight as our expected outcome of the meeting, but I think it is really important discussion. And conclusion. So the period of any motion will be inversely proportional to energy offset. And the motion is motion in space. It is not transitions between states. So superpositional states bring us to occupations on levels that are kept constant, but in Cartesian space there is a motion because it is non-equilibrium state. And this non-equilibrium dynamics in Cartesian space is occurring quicker if the energy offset is big, and occurring slower if energy offset is smaller. So let's practice. Let's practice 3 specific times when argument of cosine is equal to 0, pi over 2, and pi. And our connection between time. I will just invite you one by one to fill the table. Maybe? Yeah. Please come to the board. And the rest can have time to think and prepare. Right? Come here and draw something. So what Yungu is doing? We are. Yeah, you can try to make some happy face. So how quickly changes? Is there any time dependence for ρ11 phase factor in front of the spatial part for the coinciding for ground state?
Can I go back?
You can look at your notes
Ah,
if you were taking. Yeah, please go back.
Thank you.
Then it becomes super easy. So you got it, right?
Yeah.
The answer is still. Yeah, you can go forward. Okay, yeah. Just one half. Thank you. Thank you for being brave. Okay.
I don't know anything.
You have right to select the box in the table that looks most simple for you. Go ahead, Alfred. So, is there any time dependence for excited state for state number 2? Yes or no? Okay. So, what's the probability to find system in the excited state? If the probability to find in ground state 1/2, and total probability should be 1. Yeah. Super. Yeah, thank you. Well done. That's difficult. There are 4 simple questions and then 3 complicated.
Is that the right track?
Well, it's your process of thinking, but I need the answer. So time equals 0. What will be the sign of 0?
Oh,
So can you just write equals 1? Super. Thank you. Robin?
So like with this one, we would add on the rest of.
Yeah, and you can fill a couple of cells more because you already got the trend, right?
Oh, okay, so we got the 1/2 for each of these, right?
You can fill not here, not here.
Not there, but maybe here.
Yeah.
Okay. This one.
Yeah.
Okay. Oh. That's
Yeah. Thank you.
all.
Yeah. Okay, so now 2 tough questions for Kristen and for Alice. Kristen? So we do have a cosine.
Right.
And cosine of such time that will give us argument of cosine of pi over 2. Not argument, but cosine of pi over 2.
This is cosine then?
Cosine of pi over 2. Eventually, yes. Yeah. And we need result. I'm so lazy that I don't want to take this cosine myself. Super, thank you. Yeah. And last but not least, the toughest question. Super, immediately, very good. So you've got the idea, right? So now we are seeing partially seeing benefits of density methods. So the spatial part can be processed once and forever, and we need to focus only on the time-dependent part. Also, for some of the elements of density matrix, we see that it is trivial, and we need to focus only on the transition density. So anything in between will be like 0.9, 0.5, 0.1, and then going to negative, and then repeating the cycle. So if we explore overall expression for probability distribution for these three cases, we will get the figures that eventually will show the same as we did in the Latvian method. It will show probability distribution that you bump into left wall, right wall, go forth and back. Good. Okay. We will not finish earlier. Sorry. Yeah, from year to year, everyone does it correctly. And I did correctly too. Now, I am writing down the answer in three cases. For time equals 0, for time corresponding to phase pi over 2, and for time corresponding to phase pi. So for time corresponding to phase 0, it will be sine x squared plus sine 2x squared plus the product of sine x and sine 2x with factor 1. And note that here is 1, here is r1 half. If we go to further in time, this term completely disappears. It will be only first two terms, single hump and two hump canals. And if you go to the time corresponding to phase pi, it will be these canals and the cross term with factor -1. So what I want to do right now is to remember best part of my high school and do trigonometric simplification of first, second, and third lines, and see if I can plot them, right? Without a computer. It shouldn't be super easy, but it should be doable, because we know how to plot sines, cosines, and squares of those, right? So if it is just the same written down. I can also put 1/2 outside, right? And then it is an interesting observation. If this one can be considered as x squared, if sine of x is equal use letter a. This can be considered as b squared, and this can be considered as 2a times b. You see it? Here we can see it as a squared plus b squared minus 2a times b. You see it? So it will give a little ability to simplify stuff. Okay. So I will I will not go in the most organized way, and I will start from the middle because it is a shorter expression. What is function? What is the trigonometric expression for sine 2x? Or, I do not have verbal strength to repeat about pi over L. Sine of the double argument.
2 sine x cosine x.
2 sine x cosine x. And then with this knowledge, we can rewrite this term as 1/2 sine x squared plus 4 sine x squared cosine x squared. Right? I didn't lie. And it is great of you. Well, what should I do with sine x squared if I want to simplify my life? Can it be put out of bracket as a common term?
Yeah.
This one can go outside. And then we do have 1/2 sine x squared times 1 plus 4 cosine x squared. Close the bracket. Okay, so can I plot this function? How do I plot? Probably. Oh, okay. I should have left empty. So writing once again. Sine x squared 1 plus cosine plus 4 cosine x squared. So I want to plot this function. First, I can plot sine x squared, which will be, if here is my argument, it will be just a hum, right? You agree? For half period. It's not time, it is L. It is our box. Now, the function cosine square x, if I want to plot this function, how do I plot it? So it will be big in here, and then approaching 0 at the center, right? If you are looking for half periods. Almost nothing like this in both sides. Right? If I want to multiply it by factor 4, what should I do? I just write 4 here. Right? Right? And if I want to add 1, yeah, I am telling that my actually axis starts here, right?
Yeah.
Here is the function. Now, I do have this expression, and I do have this graph. And finally, I need to multiply them. How do we multiply functions? Graphically, if you do not have computers. Come on. What were you doing in high school?
At the
Maybe-
top.
Oh, my high school was a time when computers were too expensive. Yes?
Oh, but the top one is a half period, and the second one is the full 1 period.
No. The cosine of half period will be -1, but -1 squared will be 1. So it's we explore it from 0 to L.
Oh, yeah.
So to multiply functions without a computer, I multiply them point by point. And since I'm human, lazy human, which is natural, I select one of the specific points. Like point 0, I multiply, and here it will be 5, right? 1 plus 4. I multiply 0 by 5, will be 0. At point L, I multiply 0 by 5, will be again 0. Point L over 2, I multiply 1 times 1, will be 1. Right? So, and in between here, there will be some intermediate humps. Probably there will be something like that. Okay? And if I do the same procedure for the rest, then one will get these figures. This phase equals pi over 2 gives 2 equal humps, and with phase equals corresponds to 0 or pi, it will be leaning towards left or towards right. And anything in between will be going forwards and backwards. So we went through a lot of counterintuitive things, but now we are hitting human intuition. So we have a wave that hits one side, then other side, and oscillates force and back. Right? Just run. Well, you saw this movie. Done. Thanks for the questions, and looking forward to see you Wednesday.